Our first speaker today is Meir Hemmo from Haifa University. And he has asked everybody else all these questions in the course of his workshop, so this will be your opportunity to get even with him. And today he will talk about the direction of time and time reversal invariance.
I'd like to thank the organizers, Michael, Michael, and Yuval, for organizing this workshop, which is a very, very nice opportunity for us to exchange ideas and so on in Israel, which is a bit off the center in these fields. And also, I want to thank you for inviting me. It was, we had very nice days, I think, with plenty of points or contacts between of ideas, and it was very nice. So thank you for that. And I also want to say, before I start, that more or less everything I'm going to say here is a result of a joint work that I'm doing with Dr. Orly Schenker from the Hebrew University, who is not here now. And we are writing a book about statistical mechanics, and the stuff I'm going to talk about here is part of this book. And hopefully the book will come out next year in Cambridge University Press, so you don't need to write anything. It will be summarized in the book. Well, anyway, okay. So the talk is about the direction of time, which I take it to be effect of experience. Namely, it is a fact, I think, more or less an irresistible fact that time has a direction, and there's ample empirical support for that. As I said, it's a fact of experience. For example, one of the main things that I think support this idea is that we have memories, and the memories we have are, if we think about time as having two directions, backward and forward, then the memories we have are only memories in one direction of time, which we call the past. And so, nobody can be said to remember the future, as a matter of fact, except maybe in science fiction stories and stuff like that, but as a fact of experience, nobody remembers the future. Some of us don't remember the past very well, but in general, when we have memories, they are of the past. And that's a fact. And the question, which I think is persisting in this context, is how could current physics support this idea, this fact, or how could current physics be understood in a way that is compatible with this fact? It turns out that there are some problems about this, and I'll talk about them as I go on. But this is the question I want to put forward, namely, there is a fact about the direction of time, and the question we are putting forward is how to understand physics, current physics, physics as it is today. And when I talk about physics, I will say it more explicitly later, but I mean the fundamental theories of physics, namely mechanics, classical or quantum. I'll mainly talk about classical mechanics, but I think that same reasoning throughout the talk can be moved to the context of quantum mechanics as well. Relativity theory, and basically these are the fundamental theories. So I'm not going to. I'll mention a lot some special sciences like thermodynamics and cosmology and other theories which I don't think are fundamental as mechanics is and relativity is. So fundamental theories. What the question is now more precisely, how to understand. The question before us is how to understand. Do you hear me? I have to do it because of the internet. Yeah. Okay, sorry. So the question before us is, how can we understand the fundamental theories of physics in a way that will be compatible with the facts that we know about the direction of time? That's the question I put forward, and the answer is that we can do it. Although, as I said, there are problems, and I'll talk about the problems in a while, but I think that the problems are more, in some sense, are more due to various confusions about the question. So I think that we can do it. We can understand physics in a way that is compatible with our memories, with the direction of time. And I'll try to convince you that this is the case without making any change to current physics, just as physics is. So the task of the talk is to convince you, after putting forward the question, is to convince you that there is a way to do it, and that it is not very peculiar, in fact. It's pretty straightforward, and that will be my task, to convince you that this is the case. All right, so that's more or less the outline of the talk. Maybe I should see how am I doing with time. Okay. How long do we have? Until when?
You started a little bit late, so I guess you would have until 10:45.
10:45.
Yeah.
With before questions.
Before questions, yeah.
Okay. So half an hour is no. Okay. All right. So usually there is I said that there are problems with reading physics in a way that gives us support to the idea that time has a direction. And the main problem, let's say, which I want to talk about here is the following. All the fundamental theories of physics have a property that, except for some versions of quantum mechanics, which I'm not going to talk about, and anyway, I'm going to focus on classical mechanics now, just for the sake of the talk. So when I say fundamental physics, I mean classical mechanics. Classical mechanics has the property that its laws, its dynamical laws, are invariant under the reversal of the direction of time. We usually call it TRI, time reversal invariance. I will explain, if I'll have enough time, in a few minutes, what this notion means in some detail, because it will be important to what I want to say. But the main, so intuitively, if the laws of physics are time reversal invariant, it means that if you reverse the direction of time, the laws of physics remain the same. And this is intuitively taken in the literature, and for good reasons, as a matter of fact, to say that physics doesn't distinguish a direction of time. It doesn't really tell us what the direction of time is, or something like that. because the laws remain the same if you reverse the direction. That's intuitively the idea. And this creates a problem, because it seems that the laws of physics don't recognize in some way the direction of time. So that's more or less creates a problem. And because of that, and again, here I'm talking about fundamental physics, and I'm disregarding some versions of quantum mechanics which don't have this property of time reversal invariance. But it is important for me to focus on theories which do have this property, because what I want to say is that even in those theories which have this time reversal invariance property, the theories can accommodate the idea that time has a direction. So that's important. Of course, if this property is not a property of the theory, if the laws are not invariant under time reversal, then it could be easier. My argument could go through easily. So back to theories which are time reversal invariant in this sense, namely the laws don't distinguish a direction for time. Because of this property, people in the physics community, there's a tradition in physics, and Dennis, I think, mentioned it in the questions session of his talk. There's a tradition, because there was a question about the direction of time. There is a tradition in physics that attempts to underwrite the fact of the direction of time by other theories, in particular not by the fundamental theories, which are TRI, but by, for example, thermodynamics, or by cosmology. I'm not going to talk about cosmology here, but I will talk a little bit about thermodynamics. So the idea is that, okay, if we cannot, if the fundamental laws don't distinguish a direction for time, then maybe we could somehow derive the direction from, say, the second law of thermodynamics, which does have a direction with respect to time, namely the direction in which entropy increases. And this is more or less, I mean, if I just loosely speaking say that the second law of thermodynamics says that entropy increases as time goes forward, then the idea is that, well, maybe we can underwrite the direction of time just by somehow relying on the direction in which entropy increases. And that makes sense in a sense, because you say, okay, maybe we cannot distinguish, but maybe the fundamental laws don't distinguish a direction for time. They don't distinguish between the forward and the backward direction. But, well, the second law of thermodynamics can do it for us. So if we just look at the direction in which entropy increases, we can discern, we can discover the direction of time, and that's going to be something like that. I think that this is the idea, okay? But if you feel a little bit uncomfortable with that, or maybe if you feel that this is not completely clear, let's leave it anyway at this, because I think that this direction is flawed, is problematic. And just to be on the safe side, if I won't have enough time here, I can say why in a nutshell. If we think about the special sciences, for example, about thermodynamics, as a theory which whatever it says about the world must be derived from the laws of physics, of the fundamental theories, perhaps together with some special conditions. I don't want to say initial, because in the context of the direction of time, there could also be final conditions. So some boundary conditions and the fundamental laws of physics. If the second law is supposed to be derived from these laws, then it's a little bit hard to see how could we derive a direction of time from fundamental laws which are directionless with respect to time. So if you feel a little bit uncomfortable, it's good but that's a very prominent tradition in the literature. Almost everybody in the philosophy of physics, when talking about the direction of time, talks about the second law of thermodynamics and the direction of entropy increase as if we can, more or less in the context I just said. So, and I think it is problematic, and I can say a little bit more about it later on. So if I don't have time, you can ask me. All right. So that's the usual. So how you? I'm going now to go for the best case. I think that the attempts to underwrite the direction of time by turning to the second law of thermodynamics, as I just said, are flawed. Although this is more or less a mainstream view, it is, I think, problematic. But there is another way to do it, which is coherent in a way, but people feel very bad about it because it doesn't seem to be good enough for reasons that you will see now. And the other way is this. So maybe before I'll present the way it goes, let me present the problem in the context of entropy and the second law of thermodynamics. Let me present the problem in a bit more precisely. Okay, so the idea is this: if we are going to prove the second law of thermodynamics on the basis or from the laws of mechanics, namely this is what we do in statistical mechanics, then because statistical mechanics has the property of, or the laws of mechanics have the property of time reversal invariance, if we have a proof, we don't have yet, but suppose we did, suppose we had a proof that entropy, from mechanics, that entropy increases towards the future, exactly as the second law states. If we had such a proof, which is based on time reversal invariant laws, then the proof would also be equally that entropy increases towards the past. I'm not going to go into details, into the exact details as to how this goes about, but this is intuitively you can see immediately why. So the idea basically in statistical mechanics, it's going to be a little bit difficult to write with this, but if we will have a proof of something like the second law, it will give us, we'll have a probabilistic proof. So we will have something like this. We will have, I'll come back to this later. We will have something like that. So I'm just here drawing something intuitively, which is supposed to, suppose that these are states which in classical statistical mechanics are called macrostates, and basically these are sets of microstates here, okay? But just intuitively, and suppose that entropy is just more or less corresponds to the volume or to the area on this board. So this is a higher entropy state, this is a lesser entropy, and this is a low entropy. And suppose that we are that in the present we have a system which is in this state. Let's call it M1, and this is so M1 at T1. Okay, that's the state at T1. If we have a proof of the second law, which tells us that the system will move as time goes forward to, so all these points, almost all of them will go to this region, although maybe some will go here, but most of the microstates, most of the points here will move to here. And we have a proof that is based on the dynamics, And if the dynamics is time reversal invariant, then it means that if we reverse the time, and so we say, okay, so I can write this like this. There's some probability, which is high, suppose we have a proof of that a state of higher entropy, M2, this is M2, at T2, given that the system is in M1 at T1, okay, suppose that this probability is high, we have a proof of that. Then, because the theory is time reversal invariant, we can say that this has to be equal to the probability of M2 at T0, which I'm supposing here is earlier than T1, given M1 at T1. T1 is taken here as the present, so we have T0, T1, T2. So M2 at T0, the probability of M2 at T2, which is high by the supposed proof we are thinking about, is going to tell us as well that it is the same probability that M2 was the state of the system in the past. That's more or less the problem. And the problem follows from the fact that the theory is that the proof is such a putative proof would have to be based on laws which are themselves time reversal invariant. Okay, so I mean you could think about it like this. Let's take time slices, say 3 time slices, and we said that this is, so we have, this is M2 here, the system is here at the present, this is the present T1, most of the trajectories will go in the future to M2, some of them won't, the proof is probabilistic, but that's going to give us more or less a probabilistic version of the second law. But if you think about, if you reverse the direction of time, you will get exactly the same conclusion with respect to the present. Namely, the system didn't start at, say, M0 by the proof, but rather at a high entropy state also in the past. So we get something very weird, which says that any present time with some entropy is time at which the entropy of the system is minimal, for any time. Whenever it is the present, you get, and this is called the minimum problem. So that's basically the problem. And the way to solve it, which I think is fine, but people usually feel bad about it, and I want to try to convince you that it isn't bad at all, that in fact it's great, is this. I'm going to, let me cite Feynman on this. Feynman from the Character of Physical Law has a beautiful paper about the direction of time. He says this. So somehow to solve this problem, namely that when we are in some present time and we think about the past, so even if we are given a proof of entropy increase towards the future, we're going to have entropy increase also towards the past. Feynman says that's a problem. This is not what we remember. We may, at this time, we may even remember that we were here a minute ago, but the laws of physics tell, in fact, are contradicted by our memory. So Feynman says, I think it necessary to add to the physical laws the hypothesis that in the past the universe was more ordered in the technical sense, namely it has lower entropy than it has now. The universe was more ordered in a technical sense than it is today. So he says, let's just add an hypothesis which basically says, look, even though we have a proof that entropy increases towards the future, and that same proof tells us, because of the time reversal invariance of the laws, that entropy increases towards the past, because this contradicts our memories, contradicts the fact of the direction of time that we have in our experience, what Feynman says, let's just chop off. I mean, you mentioned something like this in your talk. Let's just chop off all the trajectories that lead backward in time to higher entropies. And so that we remain only with the trajectories that we basically remember, that are compatible with what we remember, and that gives us the direction. That's called the past hypothesis, which, now, when I teach these things, and I can tell you this from first experience, everybody that hears this is in shock. Because people say, what? This is the way we get the direction of time in fundamental physics? I mean, I'm not talking about quantum mechanics again here. That sounds extremely silly or stupid or weak or whatever. I mean, it can't be true. And it takes a lot of time to convince people that, well, yeah, this is the case. There's nothing else physics can do if it is time reversal invariant. And, okay, so that was the introduction. Now, how long?
You have 12 minutes for you.
12 minutes, fine. 12 minutes. If we start moving fast, it might be enough. Let's move faster. So, the idea is that what I want to try to convince you now is that this seemingly stupid idea, I mean, I'm not saying that Feynman, of course, has a stupid idea, but I mean, this seemingly weak idea is not only the best that physics can, that time reversal invariant physics can do with respect to the direction of time, but actually it's a very good idea. And the reason it is a very good idea, namely there is nothing peculiar in chopping off these trajectories, even though there's nothing peculiar about it, even in the context of physics, which is time reversal invariant. And the reason is this, and that's my main argument. The reason is that, as a matter of fact, even the laws of classical mechanics, at the micro level, namely the equations of motion, Newton's equations of motion, are already saturated with a direction for time. And the fact that the theory is time reversal invariant is not really an objection to what I just said. That's my main claim. Now the question is whether I'll have enough time to convince you that it is true. So I think there's a short way and a long way. Let's start with the short argument. I mean, same arguments, but less words. The idea is this: why is it true? I mean, this is quite a radical claim, but I think it is true. And the reason is this. And this is something that I think could be important for philosophers of time to realize. But I'm just going to use it for the question of the direction of time, not of the passage of time, although maybe it could be used also for this. The idea is this: the notion of velocity, which is fundamental in the definition of what a mechanical state is. A mechanical state in classical mechanics requires two things to be complete. The position of the system. It might be a position, I mean, I'm talking about phase space here and so on, but intuitively it requires position and velocity. Velocity in classical mechanics is understood as the rate of change of position with respect to time. But it is taken as part of the instantaneous state of the system. Now, velocity has a direction in time. There's a big difference. If I say that I have a billiard ball that moves from left to right, This is it. This is part of its velocity, not only the speed, but also the direction of the velocity. Then it is crucial to know which time is earlier, at which time is earlier, in order to have a non-ambiguous notion of velocity. Otherwise, the notion of velocity is ambiguous. So if you accept that the notion that velocity is fundamental to the instantaneous dynamical state of a system, then it immediately follows that you have to put that in the mechanical state, already in the instantaneous state, there is a direction for time. That's the short argument, without details. That's the claim. Okay? This is the equation of motion with no forces, just kinematics. What I just said is true also in the case of no forces at all. It's just about the notion of velocity. And the idea is this. If we think about these as, say, frames of a movie, or time frames, or something like that. So we have time, say, going, let's not be, okay, these are the positions. Suppose I have a billiard ball that moves from one position A to another position B with some constant velocity, dx over dt. So no forces. Then, of course, by the way, velocity is defined as the limit of, well, it's a limit. Yeah, it's the limit of the rate of change, and we have to take the limit from both sides of time. But this doesn't contradict what I said, that velocity needs a direction in time in order to be non-ambiguous. So the idea is this: if we have a motion of a ball, say, from A to B, so two positions, A and B, and we want to distinguish this from a motion which goes in the other direction, not of time, in the other direction in space. From B to A, we have to have a direction in each. So these are position frames, but now I've added a direction for time in each frame, in each, as it were, in each time slice. Because I need, if I want to describe the motion of my billiard ball as moving from A to B, the claim is we have to have a direction built in these instantaneous frames. And of course, if a theory, I won't have time to go through many of the details, but we could also think about so the main claim is that there is a direction built into the equations of motion, basically. In order for for Newton's equation of motion that was written here before to be non-ambiguous, we have to put a direction for time in it. Now, so how is this compatible with the idea that the equations are time reversal invariant? Well, it is compatible. It is compatible in the following sense. So we can have various sorts of, according to what I just said, we can have various sorts of motions given one direction of time. For example, we can have a motion from A to B. We can have a different motion from B to A, namely reversing the velocity, but not reversing time. Well, we can have, and also we can have some sort of something that's called retrodiction, which is not a physical evolution, but rather sort of an inference from the present about the past, or from the future about the past. But still, everything is, that I said now, all these inferences and evolutions are compatible with the idea that in the time frames here, we have a direction, because we need it to define velocity. What happens when we reverse the time? When we talk about time reversal, a time reversal is this. We really reverse the time. So what we do, we have different time frames. Let's say mark them in a different color, maybe. It's a different universe. A different universe. It's a universe where the time frames, which have to be saturated with a direction of time, goes backward. So this is time in the other direction. It's a different universe. Maybe it's not ours. I'll talk about it in a second. And here we can do the same things, but we can describe the same kinds of evolutions, but with time going backwards in the reverse direction. These two universes, if a theory is time reversal invariant, it means that these two universes are indistinguishable. That's what it means by the laws of physics. Namely, the equations of motion, which describe accurately all the motions I described before, are going to be true equally. If they are true here, they will also be true here. That's the meaning of time reversal invariant. But this doesn't contradict the idea that in order to have a universe with a non-ambiguous notion of velocity, and therefore with a non-ambiguous notion of equations of motion in general, one has to have a direction of time. So if we think of going backward now to Feynman's past hypothesis, it's not that we put the past hypothesis ruling out or chopping out all these trajectories that we had before. Remember, we had these trajectories, and we said, well, if we start here in the present, and the theory tells us that say many of these trajectories came from higher entropy states in the past, and Feynman says, let's chop them off. And people say, why? This sounds so weak, and so on. I now want to say, this is not weak at all. I mean, we know that there is a direction of time from experience, or memories, and so on. And we also now know that in order to have a well-defined theory of motion, we have to put in to the equations of motion a direction for time. Anyway, well, it's just doesn't seem to be so bad. It's not something that we do just to say. I mean, the direction of time that we put in, as it is supported by our memories that we put into Feynman's hypothesis, the direction of time is not ad hoc. It's not only to save the past as we remember it, but rather we've put it already when we wrote down the laws of motion anyway. Of course, there still remains a question which I didn't want to go into, which is related to the issue of time reversal invariance, and which is more philosophical and less. I don't think that physics would be able to settle. And that's a question which resembles the dispute between Leibniz and Clarke or Newton. Namely, so we put a direction. Suppose that this is the direction we put. This is our universe. Here is another universe. It will satisfy the same laws of the fundamental physics. Perhaps thermodynamics would not be a theory a valid theory in this world. Not perhaps. It won't be, probably. But what do we do? Suppose if we disregard the thermodynamics, what do we do? So, Leibniz would say these are the same world because the laws don't distinguish, the fundamental laws. And Newton would say no, but there is a direction of time in the equations of motion, so this is the universe, and that's it. And there's a sort of a metaphysical dispute which I wasn't aiming to solve. It is enough for me that I could push the problem of, say, the tension between the question of the direction of time and time reversal invariance to such a high-level metaphysical dispute, I mean, that's enough for me. And it seems to me that it is enough if we settle for. I mean, it seems to me that we can understand the past hypothesis, for example, in this context, not as an ad hoc hypothesis which saves the past or the direction of time, but rather as something that is more or less the most natural thing to do in a theory which has already a built-in direction of time in the equations of motion. Do I have 1 or 2 minutes more?
Minus 2 minutes.
Minus 2 minutes? Okay, so I'll stop here. I mean, I have some more things to say about the attempts I was talking about before, and I just want to emphasize that, well, I mean, I'll just stop here, actually. Thank you.
Thank you. Okay, so we have a little bit of time for questions. Dennis?
I'm not sure that I understand the argument. It's true that you need a direction of time, but there's no deferred direction of time. So without going to another universe, I could just as well take the other direction in time in this universe. All the laws would hold.
Yes.
The same way.
Yes. Yes.
But it doesn't introduce any asymmetry.
No, I agree with that. I'm just saying this is a kind of a Leibniz dispute. I mean, the question remains. I mean, of course, suppose that we don't consider thermodynamics now. We just consider the fundamental laws, which are time reversal invariant. Then you have these two universes. Of course, it cannot be the same universe because time has a direction. That's the main point. In each universe, time must have a direction, otherwise you won't have dynamics. You won't have a well-defined...
But it can be any.
It can be both of them, yeah, but that's what I said. So the main point is first to realize that the time frames, the basic microscopic states have a built-in direction of time in them. From the start. Physics starts like that. I mean, you don't have a theory, you don't have a mechanical theory without that.
Well, you choose the direction.
You choose the direction.
And then you have to stay.
But you could
have chosen the other direction.
You could have chosen, that's correct. But what I want to say, but that doesn't matter. You have to choose the direction. That's the point. Because, I mean, at least for me, when I was a student, I understood the problem of, the issue of time reversal invariance as if it said, you don't have to choose any direction. There's no direction in physics. What I want to say, no, there is a direction. It is just that, insofar as the fundamental physics is concerned, if it is time reversal invariant, well, it could have been the other direction. Fine, it could have been the other direction, but in our universe, there is a direction. That's what I want to say. And that's already built in the dynamics of the fundamental theory without going to thermodynamics. You don't need to derive the direction of time from something else. You have it already in, you could epistemically, for example, maybe distinguish between these two universes if you had a proof about, but note that no proof which is based on the dynamics of the second law, for example, would give you a direction in time, because the dynamics is PRI anyway, as I said before. So that's a silly idea, in my opinion. I just don't see what people are trying to do here. What Feynman is proposing is coherent. But people like Hawking and others who say we can derive the direction of memory from the direction of entropy increase and stuff like that, that's a non-starter. There is no way to do it. This is what I meant when I said in the discussions before, it's a sort of a PR of physics. Physics has a direction of time in this context already. Quantum mechanics without collapse, same thing. It has a direction because the mechanical state, the quantum state has a direction in time. That's the point.
Okay, we have a gentleman in the back and then draw.
Yeah. We've had long long-standing discussion on that, and I'm one of those who don't think that the past hypothesis is silly, but I definitely think it's wrong. So,
I don't think it is too. I wanted to start.
Okay, but I think Dennis has a serious point here. The point is not just directionality, but symmetry. And these are two different things. You could describe time reversal invariance in our universe without ever reversing the time, going only forward in time, and obtaining a claim about our world that is non-trivial. That is, reverse the velocities, go forward in time,
Right.
keep going, same direction,
Right.
and you end up in a state that is identical to the reverse state of your
Imposition.
conditional position. Imposition.
Yes.
That is not trivial and will not be taken care of by what you're saying here. There's absolutely no reason to believe that in the
But when you
reverse universe,
but wait,
you end up in the
alone,
same position.
but look, I accept everything you say. It's an open window. I mean,
But I'm saying it
Wait.
will solve the minimum problem in thermodynamics.
no. The way to solve the problem is by introducing the partial hypothesis. The question is only whether, and in what sense, the hypothesis is strong, is plausible, and it's ad hoc and stuff like that. That's the question. That's the meta question here. I think that the only way to go, if we don't invoke some other theories, and I don't see. I mean, these are the fundamental theories we have, and if this is going to be more or less like current physics in the future, then this is the way. The Feynman's way is the best way to do it, and I think it is a good way, but we have to understand it in the right ways. What you said about velocity reversal or velocity reversal is correct, of course, but this has nothing to do with the reversal of time. Maybe when the following thing, which I agree with as well, the fact that the theory is time reversal invariant is important not only for discussions in metaphysics about other universes, but of course it is important about, it tells us a lot about facts in this universe. I agree with that. For example, the fact that our theories are time reversal invariant mean that since in this universe the laws of physics, in the time reversed universe, the same laws hold. This is not our universe, but the laws hold also in this universe. That we can learn something about our universe from this fact. This is the fact of time reversal invariance, and we can learn from it something about our universe. Namely, in this universe, thermodynamics will not hold. If entropy increases towards the future in our universe, it will decrease towards the future in this universe. So we can learn, since the same laws hold in both universes, we can learn that there's not going to be any proof universally valid of the second law of thermodynamics in our universe, because it's going to be based on the same laws which hold here, and here we know that entropy decreases towards the future of this universe, namely downward. That's something we can learn, of course. I mean, it's a very important thing, but we have to understand the notion in the right way. That's what I'm saying.
Okay, draw.
Now, what I didn't understand is if you're right with your claim about velocity, why then do you need Feynman's past hypothesis? Because as you presented it, I don't know it. So as you presented it, it seems that it relies upon what you started with, the experiential fact that we have memories, and memories are about the past. But if you do it from velocity, you don't.
Once you understand.
So the hypothesis would be a result of what you said about velocity. It wouldn't justify.
It's not exactly a result. I mean, the hypothesis is
no, but we're in a world that has a direction of time.
We need Feynman's hypothesis because the structure of the theory is much more complicated than what I said. Okay. I mean, the hypothesis comes into statistical mechanics. In statistical mechanics, we don't talk only about microstates and the equations of motion, but also about macrostates, which are the states of thermodynamics, basically. which are sets of microstates. And there are lots of very subtle issues about the relationship. For example, is it the case that our memory supervenes on microstates or macrostates? So lots of various, I think it is microstates, of course, because everything supervenes on microstates, as I said already many times. But so the reason, of course, once you realize that, you can say, you could write down the theory differently in a way that will be compatible with what you said. But the context is very subtle.
Michael?
I'd like to ask you how does memory work in the green world? Is it
here?
Yeah. Do you remember the future or?
No.
You have to ask the green people.
You will. You will remember.
It's a representative.
If the direction of time is a fundamental fact, and which I think it is, in the physical universe, then in this universe, the fundamental fact is these little blue arrows, and in this universe, the fundamental fact is these little arrows. And therefore, and if memory, nobody knows exactly how it, I'm not pretending to know anything about, how physics can account for our memories and stuff like that. But if, I think it is plausible to say, something which is quite trivial actually, that memory supervenes on the microstate, on the microstate of the universe, or my brain, or something like that, okay? If that state has a built-in direction of time, that you come now to get a very nice and trivial explanation of why we remember the past and not the future. Because in our states, of course this is very rough and so on, and you have to think about, is it the case that memory is a computation or not? I think it is not a computation, but something else. There are lots of issues here, but I would say yes, memory, we remember the past because our states, the microstate of my brain, suppose that my memory supervenes on my brain state, the microstate of my brain state has a built-in direction of time in it. And it is just the fact that somehow, we don't know how to explain that, we remember this side. Whereas here, say Orly, maybe Orly lives in this universe with the reversed direction of time. She will remember her past.
No, she will start to remember everything and then forgetting.
No. She will.
Otherwise, what you just said makes a difference between what you said about entropy and what you said about memory. The change in the world, when you lose entropy, you also lose what we usually think about memory. It's the reversal of the film. So you start by remembering, and then the process is what gives the direction of time, the direction of forgetting, and not remembering.
I don't think it will be in this universe, but that's, I don't think, the connection between memory, direction of time, erasure of memory, and stuff like that is very subtle. I don't think it has anything intrinsic to do with thermodynamics, even though people do think that it does. It's a mistake. There's no connection between these things. I know that Dennis may oppose this, but that's what I think.
Okay, I'm afraid time's up, so let us thank our speaker again. Now I propose that we take a 2-minute break for those of you who have urgent needs to attend to, but it's 2 minutes. We're going to lock the door, so hurry up.